In this section, we'll see how radicals, which are roots, relate to exponents. So this section's titled Rational Numbers as Exponents. And we'll have a few new exponent rules, and they'll be important later. They don't make a whole lot of sense. For example, if you just look at this first exponent rule right off the bat, it says if you have something to a fraction power, which is kind of confusing. You can kind of imagine, like, what if you had 2 to the 1/3 power, That's so the base a is 2, and then the fraction is 1 over n, so I guess n is 3. That doesn't really make a whole lot of sense as far as our old understanding of exponents. Because an exponent, usually we think of that as, this means you're multiplying 2 by itself this many times. But how do you multiply something by itself 1/3 time? So it doesn't really make sense as far as our old understanding of exponents go. I think mathematicians just kind of made up these rules in a way because they kind of make sense with all our other exponent rules. And it kind of makes things easier as well. So I guess don't think of these rules in the old-fashioned way where we said, oh, this means we're raising something to a power, so it's that thing times itself a certain number of times. It won't really make any sense. So just to read this rule here, it says, if you have something to a fraction power, like a base a to a 1 over n power, that really means you're taking the nth root of it. So in that example that we had written, if you had 2 to the 1/3 power, all that really means is you're taking the cube root of 2. So whatever the denominator is, in this case it was 3, that's the type of root you're placing over the base of the exponent, which was 2. So again, doesn't really make a whole lot of sense as far as exponent rules go. Kind of just have to memorize it in a way and use it. So here's an example. If you have 25 to the 1/2 power, since the denominator of that exponent is 2, you're going to be taking a square root, or an index 2, root of 25. And that happens to be something that we know. The square root of 25 is 5. Although if you're kind of thinking, that doesn't look right, what's the square root of 25? Usually you don't see a 2 index there. So if you wanted to, you could just say, oh, if you have an index 2, that really just means regular square root. This doesn't look right, huh, when you see the square root of 25 with the 2 as an index. But it means the same thing, so you could just rewrite it. So let's practice a few of those and get the hang of it before we move on to the next exponent rule. Alright, so in example 1 part A, we have here 32 to the 1/5 power. So it just takes practice. That just means the denominator is 5, so you're taking a 5th root of whatever whatever the base of the exponent was, so 32. And then kind of going back to the old rules, you say, all right, that means you're asking yourself, what can you multiply by itself 5 times and get 32? And if you just start guessing, let's say, could it be 1? No, it can't be 1. 1 times 1, on and on 5 times will still be 1. Maybe I'll try 2. Is 2 to the 5th power? Or, if I multiply 2 by itself 5 times, is that 32? And it actually is. 2 times itself 5 times is 32. So that means it must be that the 5th root of 32 is 2. So that guy. So it's kind of strange to think about, but that means that 32 to the 1/5 power is 2. Seems strange. But oh well. Let's try the next one here. So notice that this one's negative 64 in parentheses to the 1/3. So that means that not only is the 64 being raised to the 1/3 power, it's also the negative as well. And since the denominator of the power is a 3, it'll be a cube root. And since the negative is also being raised to the 1/3 power, it won't just be the 64 inside the root, it'll also be the negative. And this is where if it's been a while or you kind of forgot, you say, wait a second, a negative inside a root, isn't that bad? Well, if you remember that since this is an odd root, it's a index 3, it's okay to have a negative in there. It would only be if that index was a 2, 4, 6, 8, etc., an even number that you'd have to worry. So I can just ask myself, is there a number that you can multiply by itself 3 times and get negative 64? And there happens to be negative 4. Because negative 4 times itself 3 times is negative 64. So it's kind of a strange one too, just to think about. Negative 64 to the 1/3 power is negative 4. So it doesn't make a whole lot of sense. Like I said, it just kind of something you have to memorize, sort of. All right, let's see part C now. Notice the negative on the 81 is not in parentheses as it was in part B. Part B had negative 64 parentheses, the whole thing to the 1/3 power. But this one, since the negative is not in parentheses, the only thing that's going to be inside the root is 81. The negative will be outside, because the negative isn't the thing being raised to the power. And then I asked myself, okay, what kind of root is this going to be? Well, that the denominator of the power is a 4, so it'll be an index 4. And I'll just think to myself, okay, well, the negative's outside, so I'll just carry it along in my answer. Now I just have to think, what's the 4th root of 81? Or in other words, what can you multiply by itself 4 times and get 81? I think it would be 3. 3 times 3 times 3 times 3. There we go. All right. But notice that if this, let's say just for fun, just to talk about it, if this had parentheses, if it was negative 81 parentheses to the 1/4, excuse me, that would mean that you're placing the negative in the root as well. So it would have been the 4th root with the negative inside with 81. And that would have been imaginary, because you notice that that index is an even number. So there are times where these will result in an imaginary answer. It's only when the negative is going to go inside the root because of parentheses, and you have an even denominator, because that would mean you'd have an even index. All right, now the last part of this example, it's a variable. So it's actually, it looks scarier, but it's actually going to be easier, because they just say simplify it. And I think in this one, all they really want us to do is rewrite it as a root. So okay, a 1/2 power, that means a square root. So index 2 of the thing that's being raised to the power is x. And then this one, I'd say you probably wouldn't leave it like that, because we know that if you have an index 2, usually you don't even write the 2. I just leave it as the square root of x with no index. And because I don't know what x is, there's no way for me to take its square root. So really, that's all I can do. So it's actually easier. All you have to, pretty much when it's a variable, all you have to do is rewrite it. And there's not really a need to simplify it. Well, actually, you can't simplify it. All right, hopefully those made sense. They just kind of take some getting used to. It's just one of those weird rules you have to memorize. They don't make a whole lot of sense. It's just that they kind of fit in with all our other rules pretty well. And this next exponent rule, it's very similar. It's just adding one sort of little layer of difficulty to it. So that's our rational exponent rule number 2. And if you compare, notice the difference between this rule and the last one is the numerator here. The last rule almost had the same thing. It said a to the power of a fraction, but the fraction looked like 1 over n. But now we're saying, well, what if the numerator is not a 1? It could be something else, like a 2, a 3, a 4, etc. But you notice, other than that, the same things are happening. If it was a to the power of 1 over n, that would be the nth root of a. So there's still that portion there, but we have this extra little bit that if your numerator wasn't a 1, if it was an m, whatever m happens to be, then that's going to be an exponent on a. So it's kind of like, yeah, you're thinking, what? You're thinking, it's like the denominator n becomes the root's index, and then m, which was the numerator of the power, it becomes an exponent on the base. So yeah, if you have a denominator and a numerator in your exponent, and the numerator is not a 1, it's something else, then you're not only taking a root based on the denominator of that exponent, you're also raising it to a power. And you notice there are kind of 2 parts to this. It says first, a to the power of m over n is the nth root of a to the m. But then there's another equal sign that says also it's equal to the nth root of a in parentheses to the m. So what's the difference between those two? I guess notice that in the left one, this nth root of a to the m, it looks like the m, the numerator m, is directly on the a, and then outside of that is the nth root. Whereas in the second part of this equal sign, it seems like the thing that's directly on a is the nth root, and then the m power is going on later. So what this is really saying is just saying, all right, you have to apply an nth root, and you have to apply a m power, but it doesn't matter which one you do first. You could do like this first one says here and say, okay, I'm going to raise it to the power of m first, and then take the nth root. Or you can do like the second one says and take the nth root first, and then raise it to the m power. And I'm going to say that in most of the problems that we'll see, probably the most useful one is the second one. So I'd highlight that guy. It's true that you could write it as this first one, but I'd say that's a lot less useful. So I'll cross that one out and circle the one that's kind of more useful. Maybe when we do an example, we can talk about why the second one's a lot more useful and easier to use. So let's try example 2, part A. Looks like we have 27 to the 2/3 power. So remember that the numerator of the exponent, numerator, is going to be the power. You don't have to write this down. This is just kind of, if you kind of think you might forget, it's kind of helpful to remind yourself. The denominator is the index of the root. So I know I'm going to have some kind of root. 27 is going to be inside, because that's the thing being raised to the power. So I have to ask myself, okay, which one is the index of the root? Is it the 2 or the 3? Well, like we said, the denominator is the index, so it's going to be a cube root. And like we said before, it's going to be easier to do the second the second part of this exponent rule where you raise it to the power outside of the root. And that's all because it's easier to take a root and then raise to a power rather than raising to a power and then taking a root. So maybe we'll talk about why after we kind of finish this problem here. So in the inside of those parentheses we have a cube root of 27. And I think about that, okay, is there a cube root of 27? Yeah, actually that's a 3. Because you're asking yourself, what to the 3rd power is 27? That would be 3. But the thing I haven't taken care of yet is that second power on the outside, so I'll carry that down. So then all it comes down to is what's 3 to the 2nd power? 3 times 3 is 9. So the whole answer to that part is 9. And let's think, just for fun, just to see why it's better that way. You don't have to write this down, it's just, if you want, you can kind of observe or something. If we did it the other way around, 27 to the 2/3, where we rewrite it as, it's the cube root of 27 to the 2nd power, but we can write the 2nd power inside if we wanted to. Because that's what the exponent rule says, the very first way they wrote it. That would mean you're squaring 27 first, and then you have to take the square root of that. Let me see, what's 27 squared? That's a huge number. 27 to the 2nd power is 729. And it's not very fun to try to think about that. What's the cube root of 729? What times itself 3 times? You know, so I think that's why it's better to do it the other way, because when you take a root of something like we did, like the cube root of 27, it makes it smaller. It's easy to raise something small to a power. But what we did just here in the green writing is you squared it first, which made it huge. It's hard to take a root of a huge number, so I guess it's better to do it the first way we did it, because you're making something smaller and then making it bigger, as opposed to making something smaller by raising it to a power, as opposed to raising something to a power, making it bigger, and then trying to make it smaller with a root. It's easier to deal with smaller numbers, and that's why the first way is easier. All right, let's try part B here. So really, I think the biggest struggle is remembering which one's the index here. But I know which one's going inside, 4. The base of the exponent is always going inside. But I always forget, okay, is it the 5? Is it a 5th root or a square root? Is it the numerator or the denominator? You just kind of have to force yourself to remember that the denominator is always the type of root, and the numerator is always the power that's going to go outside after you take the root. So let's take the square root first. And that always bugs me for some reason, because you're not used to seeing a 2. I'm just going to write it as square root of 4 with no index. So let's see, the square root of 4 is 2, since 2 squared is 4. But then I have to carry down the 5th power. Now once I raise 2 to the 5th power, I'll be done. 2 to the 5th power is 32. There we go. Alright. Doing pretty good here. Like I said, I don't think it's very difficult. It's just the difficult thing is trying to memorize what that means and which one is the index and all that. Part C, it looks like we have a negative inside the parentheses again. So whatever happens, I'm going to have a negative along with the 8 inside the parentheses. And then I have to remember, is it the numerator 7 or the denominator 3 that's the index? Well, it's always the denominator, so it'll be a cube root of that. And then the exponent is going to be 7, the numerator of the fraction. But of course I want to take the root first. What's the cube root of negative 8? Can I do that? Yes, because the index is odd. So what times itself 3 times is negative 8? That would be negative 2. And then I just ask myself, negative 2 to the 7th power would be what? let's see, I gotta think about that. I think it's negative 132. Yeah, is that right? Fine. Yeah, I think so. Oh, never mind. What the heck am I talking about? 128. Hello. I'm losing my mind over here. 128. And why is it negative? Because you're multiplying a negative number by itself an odd number of times. Yeah, so when you, I guess the two pairs, or a pair of negatives will cancel each other out. But since this is an odd power, 7, there'll be one last negative to make the entire answer negative. Alright, let's see part D here. We got negative 36 in parentheses. Okay, so first of all, I know that whole thing is going to be what goes inside the root. I don't know what kind of index it is yet, but I know since the negative's in parentheses, that'll go inside the root. And I remember that the denominator of the power 2 is going to be the index. And then the numerator will be the exponent outside, so 3. And this, so I have a square root. I always just rewrite it without the 2 because it looks weird to me. I'm not used to that. But now I remember that's a square root of a negative. It's going to be imaginary. And that's because the index is even. So in part C, it was okay to have a negative inside the root because we had an odd index. It was a 3. But this time we have an even index, so I have to worry about imaginary numbers. And it would be imaginary because now we have a negative inside the root. Alright, and we'll see in a couple sections what to do with these imaginary numbers. From at a certain point toward the end of this chapter, we'll be able to actually write out what does that imaginary number look like, and we'll study those in more detail. But for now, we'll just say imaginary. Alright, now let's look at the last part of this guy. It's negative 36 to the 3 halves. But this time you notice the negative is not in parentheses. So whatever happens, the negative will not go inside the root. It'll just be negative and then some kind of root of 36. This one has the same fraction power, so the denominator will be the index. The numerator will be the power. And this time, since there's no negative inside the root, I can actually simplify this. It won't be imaginary. So it'll be the square root of 36, which is 6. But then don't forget, you didn't raise it to the power yet, 3. So 6 to the third power, I believe that's 216, yeah. Oops, 216. There we go. There it is. A lot of these answers seem to be negative, huh? That's interesting. Oh well. Alright, so again, this is like, I don't know how difficult it is. It's just hard to remember what the exponents mean. A fraction exponent is that which one's the index, which one's the power. It's hard to memorize that. And then it's just a bunch, once you kind of translate it into an index and a power, it's just like the material from the last section. So as long as you understood the last section, once you kind of rewrite it, it should be fine. So alright, we have, don't worry, only one more exponent rule here. And it's not really a new exponent rule, it's kind of just combining the last exponent rule we just saw with an old exponent rule we already knew. So if you remember, when you have something to a negative power, remember that just means 1 over that thing. And we already knew that the denominator would be the index, the numerator would be the power. So it's not really anything new. Like I said, it's just using that last exponent rule and the fact that anything to a negative power means 1 over that thing. Yeah, so it's not really that interesting or anything. It's just reminding us of an old rule. Alright, let's just test it out and see how we can simplify these things here. So example 3 part A, we have 64 to the negative 1/3. Actually, since there's a few things going on, there's a negative, there's a 1/3. Maybe you want to do one thing at a time. For me, I usually take care of the negative first. So I just kind of remember, a negative power, that means 1 over that thing. So I'll write 1 over 64, but now to the positive power. Because once you write it as 1 over something, that means the negative's already taken care of, because that's what the negative meant to do. And then once I get to this stage, then I'll remind myself, okay, what does that 1/3 power mean again? Remember, this is the first exponent rule. If the numerator is just a 1, there's no need to do anything with that. It's just the 3 that matters. This will mean the cube root of 64 in the denominator. And then kind of it's 1 over, and you're just working on the denominator here, whatever that simplifies to. The cube root of 64 is 4, since 4 times itself 3 times is 64. So okay, that means 64 to the negative 1/3 power is 1/4. Interesting. I guess whenever you see a whole number to a negative power, you know your answer is going to be a fraction, because a negative power makes something into a fraction. So same thing in part B. I see a whole number 32 to a negative power. I know my answer is going to be a fraction somehow, but I'm going to go in stages like we did in the last one. I'm going to take care of the negative power first. 32 to the negative 2/5 means 1 over 32 to the positive 2/5. And I'll worry about the 2/5 later. I just want to take care of the negative kind of first. Once I'm here, then I try to remember, okay, now the numerator is not a 1, it's a 2. I mean, by that I mean this numerator here. So I say, okay, it's going to be some kind of root of 32. Is it a square root or a fifth root? Remember the denominator of the power, 5, that's the index. And then, the numerator is going to be the power outside that. So I have 1 over the fifth root of 32 all to the second power. But like we saw before, I'd rather do the root first. The fifth root of 32 is 2, because 2 to the fifth power is 32. But don't forget you had a little square outside of that. So my last step is to do, what's 1 over 2 squared? That's 1 over 4. So really the answers to part A and part B are the same. Interesting. Alright, let's try part C. So this one, I have a feeling, when there's variables involved, it looks scarier, but usually in these root problems, that means there's not as much work you have to do. So that'll be the same, or that'll be true in this part, and I think the next couple parts. Now notice that you have here 3xy, the entire thing, to the power of negative 4/3. That means that whatever kind of root is going to happen to this thing, 3xy, that entire thing is going to be inside the root. But like we did in the previous problems, I'm going to take care of the negative first. The negative exponent means 1 over that stuff to the positive power, so positive 4/3. And then I'll take care of, what does the 4/3 mean? Okay, well, I'm going to take a cube root, because that's the denominator of the power, of everything that was being raised to that power, 3xy. And that whole thing is going to be raised to the 4th power, because that was the numerator there. And really, there's not a lot you can do with this. I don't know. You can probably just leave it like that, because I can't really simplify that. This would be, what do we have to do first? We'd have to say, what's the cube root of 3xy? Well, there's no cube root of 3. I don't know what x is, and I don't know what y is, so there's not really a whole lot you can do here. I'll probably just leave it like that. So keep that in mind. A lot of times when there's one variable or multiple variables involved, usually just rewriting it is as far as you need to go, because there's not really much you can do with the variable since you don't even know what it is. So I have a feeling that'll be what's happening in part D. Notice in part D they're kind of trying to confuse us. Part D has the product of 3 things here. There's a 7, that's being multiplied by a to a negative power, and that's being multiplied by b to the positive power. So there are 3 things being multiplied here, and if you remember from previous sections that we're kind of reviewing exponent rules and we saw negative exponents, remember that only something with a negative power has to move. So since the 7 doesn't have a negative power, it's not part of that thing being raised to the negative power, it's going to stay as is. Same thing with the b. He has a positive power, so he doesn't really need to change. But the a has a negative power, so he'll be changed to 1 over that thing. 1 over a to the positive 3/5. And just to remind myself what's happening between them, I put little multiplication signs. And I think I should probably multiply across here, I guess. I'm going to put these over 1. 7 over 1. 1 over a is already a fraction. I'm going to put the b over 1. And if I multiply across, I'll have 7 times 1, which is 7, and then b to the 3/5, over 1 times a times 1, that's just a to the power, oh wait, 3/2, sorry. I kind of stole b's power, huh? I forgot, or I didn't notice. A had a power of 3/2, not 3/5. Okay. And I think the last thing you would do here, since they said, what is it? They want you to use radical notation. And remember, radical means root. So if you don't end with the root in your answer, then something's wrong. All they want you to do is translate, for example, b to the 3/5 into a root. But remember, that means the 5th root of b to the 3rd. And the same thing in the denominator. We have the denominator of the power, 3/2, the denominator is 2. That means I'm going to have a square root of a all to the 3rd. There we go. And that looks, at this point, since I know I can't simplify that, if you want, you can rewrite it the other way. Bring that power inside the root, because it looks a little prettier. So you might see that in the homework as an answer. Instead of the fifth root of b parentheses to the third, you might see them write it as the fifth root of b to the third. Just looks simpler because there's no parentheses, I think. And then the same thing in the denominator, square root of a cubed instead of the square root of a parentheses cubed. Alright, let's try the last one here, and then we'll move on to kind of putting a bunch of exponent rules together, just trying to remember all those crazy exponent rules. Let's see, part E. Okay, this is kind of a reminder that I've seen this before. If you have a fraction to a negative power, you flip it upside down. Because you notice we have a fraction, it's 9c over 2d, and it's being raised to a negative power. Power is flipped. So you use the reciprocal of that fraction instead. So instead of 9c over 2d, I'm going to write 2d over 9c. And once you flip it, then you don't need a negative power anymore. It'll be positive 2/7. There we go. So that's kind of how you take care of a negative power on a fraction. Parts A through D, we didn't see any fractions being raised to a negative power. But this time we do. And now that I have it with a positive power, the last thing they want me to do is rewrite it in radical form. So I just have to take notice that the entire fraction is being raised to the power. So that entire fraction will be what's inside the root. And is it a square root or a seventh root? Remember, the denominator is the type of root, index 7. And then I am being raised, or this whole thing's being raised to the second power. You could put the second power outside, but I imagine if I put the second power outside, I wouldn't be able to simplify the seventh root anyways. So usually if you can't simplify, you put the power inside, just because it looks prettier that way. So I'm going to say it's the seventh root on the outside, that whole thing to the second power inside, and the second power comes from this 2 up here, the exponent, or sorry, the numerator of the exponent. And you know what, I think this can actually be simplified because you have a whole big fraction to the second power. You can kind of distribute that power onto everyone. 2 squared, d squared, 9 squared, and c squared. 2 squared, d squared, 9 squared, c squared. And I'd say the very last step would just be, you can square those numbers. 2 squared is 4. Well, I don't know what d is, so I can't square it. 9 squared is 81. And then c squared, I don't know what c is, so I can't really square it. That's probably as good as it gets. That's probably as difficult as those get. I think a lot of times the hard part of these is knowing when to stop, When am I done? Can I stop now? I'd say if you ever end with parentheses, that might not be great, See if you can do anything else, I guess. Alright, hopefully those exponent rules are sinking in, but we'll have a lot more practice here with these last couple problems. Alright, let's see. So this one we're just going to try to use the above 3 exponent rules that we just learned, and then maybe old exponent rules that we already know to try to simplify these last couple problems here. So let's see, part A. Notice you have a base 5 to a fraction power, and you're multiplying it by a different base 5 to a fraction power. But if you remember, there was an exponent rule that said something like a to the m times a to the n. If you have the same base to different powers and you're trying to multiply them, you add the powers. So that's what we're going to do here. Even though the powers are fractions, we're still going to add them. So these guys can be combined into 1/5, or the exponents you're going to add 1/4 plus 1/8. But notice those are fractions you're trying to add, and they don't have the same denominator. So unfortunately, you actually have to get a common denominator to add. Between 1/4 and 1/8, the common denominator would be 8. I'll have to multiply the first fraction by 2 over 2. That way they'll have the same denominator. So it'll be 5 to the power of, that first fraction becomes 2/8, plus the second fraction already had an 8 as a denominator, so it was perfect, 1/8. Now I'll add those guys, 2/8 and 1/8 is 3/8. There we go. And sometimes on these ones it's hard to tell, do they want me to end here, or do they want me to rewrite it as we saw before, that means the 8th root of 5 to the 3rd. I don't know, I think a lot of times, if they don't say, what were the directions in example 3? They said, write an equivalent expression using radical notation. So notice that they specifically said, use radical notation. In other words, put a root in your answer. They didn't really say that in this one. They didn't say use radical notation, so I think we'd probably be okay leaving it this way. The only reason I would change it maybe to the root notation is if I had a hope of trying to simplify that. But there's no way I'm going to take the 8th root of 5. And even if I cube 5, 5 times 5 times 5 is 125. So I could do that. But there's no 8th root of 125, so I don't know, it'd almost be pointless to rewrite it. I don't think I would. I'd just leave it this way. And again, they didn't tell us to rewrite it, so it's not, I don't know. They'd probably tell you to rewrite it as a root if they wanted you to. I think these are just more practicing your exponent rules, not really trying to simplify roots. It's alright, how about part B? It looks confusing because it's 4.3, it's not a whole number. But it's something to a power over something to a power. And the bases are the same, so we can use this old exponent rule we had. It was like if a to the m over a to the n, because we have the same base, you would subtract the powers. It'd be m minus n. That's what I'm going to do here. It's 4.3 to the power of, the numerator's power is negative 1/5. I'm subtracting the denominator's power, but be careful because the denominator's power is negative. So I got kind of this subtraction sign here from the rule itself over here, but the negative exponents were from the negatives themselves. This negative is this negative, this negative is this negative. So be careful, just because there's a negative on the bottom doesn't mean you don't need a subtraction sign. You still need that. But I might rewrite it one more time because I see that it's 4.3 to the negative 1/5, but then they're subtracting a negative. I'm going to write a plus. If you see two negatives next to each other, we know it's going to be a plus. And now we're kind of down to something that's similar to the last part, part A. You're trying to add two fractions that don't have the same denominator. Well, here the LCD would be 10. So I need to multiply the first fraction by 2 over 2 to get that. So it'll be 4.3 to the power of, that first fraction will become negative 2/10, plus the second fraction is staying the same, 7/10. So let's see, negative 2/10 and 7/10 is 5/10. And even though this is an exponent, 5/10 is still a regular fraction. We can reduce it if we want. Actually, we should. 5/10 is the same as 1/2. So there we go, 1/2. And if they had asked us to, if this in radical notation would be the square root of 4.3. Because remember, the denominator is the type of root. But I think we're okay to leave it as 4.3 to the 1/2 because they never said to write it as a radical. Alright, so far so good. I think we're doing pretty good here. Let's look at part C. So here's another exponent rule that we've seen before, but now it looks, of course, way more complicated because there are fraction powers. But I think we had, what was it? It was like, if you have two things inside being multiplied, like a times b, we have m and n, and you have a power on it, you can distribute that power onto either of those things. So it'll be like a to the n, b to the n. So I'm going to say I have m to the 2/3. The power that's outside the root is 1/2. Or sorry, the power that's outside the parentheses, I'm going to distribute onto the m, and then also onto the n. Even though either of them already had a power, they're each going to get that 1/2 power. And then this kind of looks like, I've seen this before, you have a power to a power. This kind of uses another exponent rule. At this point you have, remember, if you have a power to a power, like a to the m to the power of n, you multiply the powers, it'll be m times n. That's what I'm going to have to do at this point. For m, his powers are 2/3. That's going to be multiplied by his other power, 1/2. I'll have to think about that. And then the same thing for n. His first power was negative 1/4. That'll be multiplied by the new power he has, 1/2. So for the m, notice the 2's cancel on the diagonal as I try to multiply those fractions. So it just becomes a 1/3 if I multiply across. For n, nothing cancels, I'm just going to have to multiply across. It's a negative times a positive, so it's a negative. 1 times 1 is 1, 4 times 2 is 8. So that's kind of as simple as that one gets, but I think, notice that they said in the directions, do not use negative exponents in your answers. You can pretty much be sure that all the problems that you see in, actually this whole class, if you ever end up with a negative exponent, they don't like it, so you want to rewrite it. But we know that since m does not have a negative exponent, he gets to stay as he is. But since n does have a negative exponent, he has to go downstairs. So n to the 1/8 will now become the denominator. There we go, and that looks good. And again, don't worry about trying to translate that into a root, because they didn't really ask us to. Alright, I think we're doing good. It's just a matter of trying to combine the rules we just learned with old rules that we might have forgotten at this point. Let's try part D. So we have the 12th root of a to the third. Well, I don't really know what a is, so I can't really cube it, I can't raise it to the third power. I don't know how to find the 12th root of something like a, since I don't know what a is. So I think this one, all I can really do, the only trick I have up my sleeve is rewrite as an exponent. So we're kind of going to use the exponent rule backwards. Remember above we had an exponent rule, the second exponent rule. It was a to the power of a fraction equals, let's see, the denominator is the type of root, and then the numerator is the power. But this time we're going backwards. Notice we're starting with something like this, a root of something. So I'm going to try to go backwards here. It's going to be a to some power. Notice the denominator of the power is the index. So the index of the root we were given is 12. That means the denominator will be 12 for me. And then the numerator of the power here, m is the power on a. And the power I have in the example that they gave me was 3. So you can rewrite this as a to the 3/12. And this might seem weird because usually with this exponent rule we go the other way, where maybe we're given this and we have to rewrite it like they gave us. But now that I have it like this, a to the 3/12, 3/12 is a fraction that reduces, so I can reduce that. 3/12 is 1/4. And now that I've been able to reduce it, if I want to, you could probably leave it like that, but if you wanted to, you could rewrite it as just 4th root of a, because that's what that means. Alright, so really what you can take away from that problem is, I guess if your index and your power have a common divisor, 12 and 3 both divide by 4, you can kind of divide them, like here, okay, what's 12 divided by 4? Or sorry, 12 and 3 have a common divisor of 3. If you divide them, 12 divided by 3 is 4, like we see in our answer. 3 divided by 3 is 1, so that you don't even see it here. So that's true. If your index and your power have a common divisor, you could just go ahead and divide them. That's kind of the shortcut there. Let's see, let's try the similar thing with part E. Here we have the 7th root of xy to the 14th. So it kind of looks like the 14th power is outside. But still, remember we had the exponent rule. If you have the nth root of a to the m, you can write that as the denominator is the index, and the numerator is the power. So same thing here, it's going to be xy in parentheses, because that's the whole thing is what's inside the root. It's being raised to a power where the denominator is 7, because that's the index, and the numerator is 14, because that's the power. And that reduces for sure. 14 over 7, as a matter of fact, that reduces to a whole number, 2. And even though these are exponents and it feels like maybe you can't reduce them, I think that's why they come up with these exponent rules, because otherwise I wouldn't be able to simplify this. But once I translate it into an exponent, then I can simplify it. So I think we can kind of see why they came up with these rules, because it does help us simplify things that we might not be able to otherwise simplify. So now it just comes down to parentheses xy squared. And we know that a lot of times if you have parentheses in your answer, if you can remove them somehow by simplifying, that's a good idea. And we know that if you're multiplying two things inside parentheses, and that's being raised to a power, you can distribute the power onto either of them. You could just say it's x squared, y squared. Give each of them their own square. Alright, the last one. This one looks almost like, I almost feel like I have double vision here. Am I seeing something twice? No, they did that on purpose. There's two different roots there. There's the 6th root, and then on the inside a square root. So I think this one, we're going to have to tackle it similar to parts E and D. I really don't know how to simplify this until I translate both roots into exponents. Alright, it doesn't really matter which one you tackle first. I guess I'll tackle the outside one. So a 6th root, remember the rule is if you have the nth root of something, that can be written as that thing to the 1 over n power. That was our first exponent rule. So the 6th root, that would be something to the 1/6 power. And that something that's inside, maybe I'll do it one step at a time. That something that's inside is the square root of z. So that's one thing, but I'm going to try to go a step further and write the square root as a power as well. So it's a square root, but remember that it's a square root with an invisible 2 as an index. So this would be z to the 1/2 power, using the same kind of rule over here. Alright, now that we have it down to a power, we kind of discussed this earlier. If you have a power to a power, you multiply the powers. So it'll be a 1/2 times a 1/6. There's nothing you can really do to simplify that, or reduce, right? You just have to multiply across. 1 times 1 is 1, 2 times 6 is 12. And that's really it, z to the 1/12. If you wanted to write that as a root, the denominator is 12, so it'd be a 12th root of z. So I kind of noticed if you wanted to make a shortcut out of it, you could say kind of to yourself, you know what, if you have a root over a root, if you want, you can just multiply their indices. Because notice it's a 6 as one index, a 2 as another index. What if you multiply those indexes? 6 times 2 is 12. That could have been a shortcut, because that's the answer we got in the end. But I guess we didn't know that. But now that we use the exponent rules, we know if you have a root within a root, you can combine them into one root by multiplying their indexes. But I hope everything made sense, and it'll make more sense as you practice your own problems, of course, as usual. We'll move on to more interesting things to see with radicals. We're going to soon learn how to take two roots or radicals, multiply them, divide them, maybe add them, subtract them, kind of all the operations you can do. And then towards the end of this chapter, we'll see how to simplify radicals, how to solve equations with radicals, and then as promised, we'll see imaginary numbers kind of in more detail. But okay, thanks for listening. I'll see you in the next video. It'll be fun. Bye.